thank you very much for coming today. I hope you had a good Easter break. First, let me acknowledge the traditional owners of the land, the Wurundjeri people and their elders past and present. It's terrific to have Zebedee, Nicholls and Alexander Nauels here today with us. I'm privileged to serve as both the supervisor for both of them. So, for example, Alexander Nauels came to us here a long time ago from the IPCC Technical Support Unit. And so there's a whole lot of history, not only in Alexander Nauels' path to these climate scenarios, but also to the climate scenarios in general. Who has heard about SIES scenarios? Raise your hand. Most of them, and the others are just too shy. Who has not heard about RCP scenarios? Okay, 3, 4. So you will learn about the exciting new generation. So we have SIS, which came around 2000s, 2001, the RCP scenarios, and now it's about the new generation of climate scenarios into the future. And it's not only about socioeconomic storylines, population growth, GDP on a global and regional level. It's also about all the climate information. And why is it important? Not only to steer and govern huge international climate intercomparison exercises. So, for example, running the climate model and figuring out how the Earth is reacting to our unique experiment that we do with it, and to figure out what is the uncertainty. It's also now important, for example, for issues like what the Task Force for Climate-Related Financial Disclosures came about, so that boards now in Australia and elsewhere will have to report on their climate-related risks. For that, of course, you need to break down lots of these scenarios, but these scenarios in the end will provide a very coherent structure to all this information that is about to stay with us for the coming decades, whether it's in boards, whether it's in governments, where you have the energy transition risk, but also the climate-related risks. So you will today be presented with the possibly slightly on the nerdy side, the zoom into a process that is at this point in time very much underway. And we are in the college here also fortunate to be part of that scenario design process. So, for example, we do the greenhouse gas concentrations, but it's again, and I'm soon closing my opening remarks, it's a huge communal effort. For example, there are groups on open biomass burning, there are groups on stratospheric ozone, there are groups on aerosol optical properties that all the climate models should run with. There was a huge group on comparing the different socioeconomic storylines, etc. So they're all groups around the world. We are the ones who provide the greenhouse gas concentrations both for the past and the future based on the model results that the integrated assessment models give to us in terms of emissions. So I think I talked enough again. Thank you so much, and the stage is yours.
Thank you very much, Malte, for this kind introduction. I think you've already realized that this whole scenario thing is very complex, and there's a lot of things to it, and in particular, a lot of abbreviations and all these kind of things that are potentially very confusing. So our task today, Zeb and my task today, will be to walk you through. Thank you. To walk you through what has happened in the past a little bit, and also then give you some information about the details of the shared socioeconomic pathway design. I call it pathway pasta. So if we go through the last 30 years or something of scenario development, that was the first assessment report. There were some scenarios, they had some abbreviation. There were some other scenarios in the second assessment report in 95, and it goes through. There's this, it's all like wiggles and abbreviations, and nobody really knows what's going in and out and why in particular. So, that's the third assessment report in 2001 with a different set. I think that's probably even your figure, Malte. I don't know. Yeah, from the fourth assessment report where we had a different set of scenario, the same scenario set, but a different analysis. And that was the latest one in 2013, where you can see SRES. Malte asked about SRES and RCP. So I will try to, in the first stint, to walk you through what has happened and why, and what has changed now with the new ones. So what will actually happen in 2021 with the new IPCC assessment report? I hope that I can sort of provide you with some knowledge about at least the scenario part of things. All right, so our little talk will be structured like that. We'll walk you through some scenario history, then we'll dive into the specifics of the SSPs, and that's basically almost until the end. And the specific, the special part of today's talk, I would say, is that just recently we've been able to extend the scenarios beyond 2100. So we'll provide you with some new insights on that, which is, I think, very key for a couple of climate variables. And Zeb will actually provide you with some numbers on that. So let's start in the beginning. As I said, the first assessment report already had some sort of climate scenarios. They had 4 scenarios, 1 business as usual scenario, and they were all just developed until 2100. They had, and that's interesting how that changes over time, they had the same assumptions for economic changes and population. They only varied the energy mix. And basically, the business as usual scenario was the non-intervention scenarios. The others all assumed some sort of climate policy intervention. The second assessment report used a different set of scenarios. They're called IS 92. I don't really know why. It was before my time, but they were also designed until 2100. They, compared to the first family, had varying population assumptions. The income was varied, and so it was a little bit more complex already than the first set of scenarios. And from the second report actually came this massive scenario development exercise that Malte already also alluded to already. That's the SRES, the special report on emission scenarios that was conducted under the IPCC framework. And for the first time, 4 proper storylines were developed that would sketch different futures. And from those 4 storylines that you can see, maybe, oh, sorry, from that you can see here, they basically developed 6, and that these are the famous ones down here, 6 illustrative pathways that were used for both the third assessment report and the fourth assessment report of the IPCC. I think it's important to give you a little bit more detail on that, because that also has some implications on the development of the SSP scenarios that we will be talking about later on. So they had 4 different narratives. A1, which assumed rapid economic growth, and that's where the fossil intensive pathway, the non-fossil, very renewable focused pathway, and the A1B scenario, which is, I think, the most famous SRES scenario, maybe for people who are familiar with it, stem from. Then the second storyline basically assumed a very heterogeneous world with self-reliance and a constantly or consistently increasing population. That's actually quite an important assumption that went into that one. The B1 scenario was much more positive in that it assumed a convergent world and more rapid changes towards an information and service-based economy. And clean technologies, B2 was somewhat like an intermediate scenario where local solutions were pushed, and they had also continuous population growth, but more diverse and technological change. So you can see that there's a whole lot of socio-economic assumptions going into this scenario family, and that's where, you know, people, well, I guess after the fourth assessment report, there was a need for a new generation of scenarios and update that one again. But the community realized that it's a very time-consuming effort to basically use that what's called the sequential approach. And the sequential approach, maybe it was already quite clear from what I've shown you before, started with these narratives, developed emission scenarios from that and from the emission scenarios, and that's where basically MAGIC, the model that is maintained by Malte here, comes in, translates the emissions into some sort of climate forcing. And then from that, basically climate scenarios are generated in different varieties that are used then to, in the end, make some sort of impact assessments maybe. So that's a very logical, sequential thing, but it's very time consuming. So the strategy then was to change from that approach to what's called the parallel process. It will be a pretty busy slide. You'll see it's quite nice. Actually, I like it. I hope I won't confuse you too much. So what happened was the community decided to break up that chain and start with the middle bit. Basically, take the radiative forcing assumptions that would sketch a very wide range of different climate futures with already published sort of storylines underlying that would provide the emission pathways, and from there two different pathways would emerge. So you would go climate scenario development. That's basically what happened. That's the RCP usage that we're used to over the last 5 to 10 years or so, and that's also what has been used in the latest IPCC assessment report in the AR5. But at the same time, the integrated assessment model community started to develop new storylines and much more sophisticated and detailed storylines that would be able to sketch pathways to reach those radiative forcing numbers that have been defined as part of the RCP development process. So it's like it just branched off, and now we are in a position to come back together again. So the SSP framework that we will talk about today is bringing these two things together and hopefully providing a much more comprehensive framework to analyze how we get to certain climate futures. All right. We've talked about the RCPs a little bit. I'll give you just some more details about what they actually entailed. So they were like 4 particular radiative forcing levels in 2100 were identified to basically sketch a business as usual or worst case scenario, and the best case scenarios and levels in between that would allow the climate modeling community to assess the responses of the climate system as well as possible. 2.6 is the one that would be consistent with keeping warming below 2 degrees relative to pre-industrial levels. So that was if anyone talked about that climate target with a likely chance, which is actually only half of the Paris Agreement, as we probably know, because they also have that 1.5 target in there now. But still, if they talked about that target, it was probably the RCP 2.6 that they would be using, or that would be underlying the numbers that they would be presenting. And for the first time, and that's really important for me personally, I think, because I'm looking into sea level rise for the first time, Malte developed extensions that would go beyond 2100 and allow the community to assess how climate variables that respond on much longer timescales, how they would go with different assumptions. So that's the RCPs. That's how, for example, the fossil and industrial emissions, CO2 emissions, look like according to what's been agreed on by the community. So you have basically the gray part is the 21st century. You can see the old SRES scenarios where they're sitting and where the new RCPs are sitting with regards to the emissions, and then you see like a more schematic and extension towards 2300. It's important to note that, and that's something you may have already seen, that the SRES scenarios didn't provide like a really strong reduction scenario, mitigation scenario. And that's where sort of this RCP 2.6 scenario came in. So in many ways, the RCPs had a lot, provide a lot of new information. All right, enough history. Let's look what the SSPs are actually doing. And now we have 5 storylines instead of 4. So the scope is a little bit wider, I think, with what the SSPs are as narratives are trying to sketch. Malte has already noted the integrated assessment models that are used to produce those pathways. Basically, they provide optimal cost pathways for different energy mixes, depending on what carbon price or what other assumptions go into those settings. It's a really complicated process. I don't do this. Zeb doesn't use integrated assessment models. We basically apply them. But a whole community is basically busy running models, trying to provide the right pathways for the narratives that have been defined. Key to the SSPs is the fact that the baseline scenarios, so the pure SSP scenarios, do not assume any kind of climate policy. The development until the until the end of the 21st century is purely based on changes in the energy system, or how population develops, how the divide between north and south and rich and poor develops. So there's no assumptions about carbon prices going in the first place. So we will look into the baseline scenarios, sort of the pure SSPs at first, and then continue to delve a little bit into what's been done to get us also into a position where we can assume different levels of climate policy chucked into these individual pathways. So I think this is, at this stage, I will hand over to Zeb. Is that correct? Ah, yeah. Well, I will run you through the 5 SSPs individually, and then we go from there. So SSP 1 says sustainable development. There's a key marker integrated assessment model. I'm just flagging them just to make sure that you understand that there's, I think, 5 key models that are used to provide the narratives for the pathways for each SSP. SSP2 is basically a middle of the road, a balanced scenario. We will talk a little bit more about that. And SSP3 is the one probably with the worst outcome globally, in a way that it's really, really fragmented. Regional rivalry dominates, and there's no international cooperation. SSP4 basically is a scenario which assumes a case where the rich get richer and the poor get poorer. And SSP5 is maybe the one that we're heading on at the moment. So we're increasing our energy demand, but unfortunately that increased energy demand is mainly met by fossil fuel development. So these are the 5 SSPs. And you can sketch them in a rather nice way that makes it a little bit easier, I think, in a way that you would try to put them on a 2-dimensional plane regarding the challenges for adaptation and the challenges for mitigation. And you can see the SSP is obviously in the middle, up here, and then you have SSP1, the sustainable scenario, down in the left corner with low challenges to mitigation and adaptation. On the other side of things, you have SSP3, where everything is really hard. And SSP4 is sort of down here. So there is lower mitigation challenges because there is money, but not for everyone. And SSP5 basically is sitting up here, just sort of as the opposite of SSP4. All right, so Zeb, do you want to go from here?
Thank you, Alex. So hopefully you're all still loosely with us. We've coordinated outfits to try and make sure that bit's not too confusing. So as we've seen, the SSPs are a bunch of narratives, and we've got the quantifications of those narratives by the IAM groups here in front of us. So I'm going to take a little bit of time to run through these quantifications, and as we do that, I'll try and always link back to the slide you just saw, so we start to get the storylines in our head, because there's obviously quite a lot going on. But we start off here with GDP per capita, and we see effectively here that when you quantify these storylines, the adaptation axis really dominates how your GDP per capita evolves into the future. So in a world where adaptation challenges are low, we have SSP5 and SSP1 with relatively high GDP per capita. And in a world where adaptation challenges are high, so SSP4 down here and SSP3, we have a much lower GDP per capita. And that's in particular because of the inequality which develops throughout the rest of the century. And so we really see that, at least in the quantifications, cooperation actually makes everyone richer, and these sort of regional rivalries hurt on balance. So we can see that in a bit more detail if we look at the ratio between the GDP per capita of the richest region, so the OECD, and the poorest region, so the Middle East and Africa. And we see a similar storyline that in both SSP5 and SSP1, that inequality gap really closes throughout the 21st century. In SSP4, despite the fact we've got low mitigation challenges, our adaptation really hurts and leads to this inequality persisting throughout the rest of the 21st century. Middle of the road, we have reducing inequality, which is one of the assumptions which goes in, and SSP3 kind of sits by itself up here. An important point to note here is that these GDP assumptions, along with population assumptions, are drivers of the scenarios. They don't receive any feedbacks from the climate outcomes which may result in those scenarios. So there's no climate shocks which come out, for example. So these are really prescribed assumptions and quantifications of these narratives. There's no chance for kind of any feedbacks to occur. And that's, part of the difficulty of modeling a system like, our Earth, where you've got these feedbacks in reality, but the constraints of actually modeling them mean you've got to make some choices. So we move on from the drivers into what the models actually come out with in response to those drivers. We see here total energy demand for the Earth. And here you start to see really the mitigation axis takes control. So now SSP1 and SSP5 are split. And we've got SSP5 with its high mitigation barriers leading to extremely high energy demand. SSP1 with its low mitigation barriers leading to much, much lower energy demand throughout the 21st century. In the middle, you've got SSP4 with its low mitigation challenges sitting much lower than SSP3, which is with its high mitigation challenges, and middle of the road sits kind of loosely in the middle, although not quite. And that's part of the difficulty of quantifying these scenarios in a consistent way. And one of the challenges which the IAM teams do an amazing job of is creating self-consistent quantifications of narratives which are difficult to put numbers on. We look at the renewable energy share, and again we see this split along effectively the mitigation axis, where again you've got SSP1 and the Sustainable Development Road versus SSP5. One of the interesting storylines here is that you start to see through the end of the 21st century that even in SSP5, you're basically so rich you start using renewables as well, because you just need the energy and you kind of run out of other resources. Whereas in SSP3, we've got this massive regional rivalry. That doesn't happen. We've basically all just shut up shop and decided that, we're just going to go for it ourselves, and renewable energy is not really of interest to anyone. Or at least that's what the quantifications make this look like. And then the last one, which is a big one, is the fossil CO2. And that's, one of the key drivers of climate change. And here we really see that mitigation axis dominating again. But we also see kind of the development assumptions coming in too, where SSP5, you've got effectively fossil fuel driven development, which Alex mentioned. SSP1, because of your high renewable share, and because your primary energy demand is fairly low, because you've got all these efficiency measures coming in, you've got a much lower fossil CO2. And the other scenarios sit through the middle. The other important thing to note here is that none of these emissions go negative. And most people in this room will know that if you want to meet a 2 degree or 1.5 degree target, you need to start reaching net zero emissions, as soon as possible, and ideally by 2050 or so. And so that's a really key point to keep in mind, that what we're showing here is the quantification of the baseline scenarios, and there's no climate policy in place yet. That climate policy will be introduced by Alex throughout this next section.
All right. So thanks very much, Zeb, for this detailed glimpse on how they actually look like. It's always easy to just provide some numbers, but the pathways in front of you may be really helpful, hopefully. This is a very key matrix for the whole SSP rationale, and it makes it hopefully a little bit more clear what this whole framework is about. Now, we were talking about SSPs, but it's actually, if we are more precise, it would be an SSP RCP framework. So these shared socioeconomic pathways are the narratives that we've introduced before. But obviously, the baseline scenarios, as we've learned, are not enough. So we will have to meet some kind of radiative forcing targets that have been defined previously also as part of the parallel process. So these RCP radiative forcing levels are kept and are used as indicators where we want to go with climate policy. So we go from basically the baseline scenarios that would allow us to reach forcing levels somewhere here, to go down all the way to 2.6 watts per square meter, for example. So you have, as you can see, these numbers may look a little bit familiar. You have the 8.5 watts per square meters, you have the 6.0 watts per square meters, and 2100, 4.5, 2.6. These are the old RCP radiative forcing levels. They have been expanded to allow for a more comprehensive analysis from the climate science community, but also a more diversified analysis of how overshoot scenarios, for example, impact the long-term response of certain climate variables or something like this. And we know now that we need lower radiative forcing levels than 2.6 watts per square meter in order to meet fully the Paris Agreement. And that's just recently happened, that Yuri Rogali has actually published a paper which gives us now a new radiative forcing number in 2100 that would allow us to meet also the 1.5 degree target. So we have now a much more, just a much bigger list of radiative forcing levels. And out of this matrix, where you have the storylines on the top, which we have been now talking about quite a bit, and the radiative forcing levels on the y-axis, the CM6 scenario community has selected illustrative pathways that would be used in the next AR6 assessment report, and these are the blue ones actually shown here. So the whole lot has been reduced a little bit to make it slightly easier. So there's like a really high pathway based on SSP5, which hits the 8.5 watts per square meter. Then we have an intermediate one, 7.0, 6.0, and then basically we have even two with a 3.4 target. One's an overshoot scenario. Otherwise, one's a really steep mitigation scenario based on SSP5, one's based on SSP4. And as Zeb has already said, and I've also already indicated with the forcing levels, now it's basically the time to introduce climate policy levels. So whenever you walk down on the y-axis, you introduce policy measures. Different stringency of implementation from 2020 to 2030, global cooperation, delay, depending on the narrative. So for every narrative, for every SSP narrative, a consistent set of so-called shared policy assumptions, SPAs, have been developed, and they are used to get the baseline scenarios to the different radiative forcing levels in 2100. So it's quite complicated, I have to admit, but it will give us a very comprehensive set of options for the analysis of different futures. So let's have a look at the new thing down here, the Paris Agreement consistent pathway. This just actually should show you how it works from going from a baseline scenario, which is on top, to like different forcing levels. So this is basically how the actual pathways could look like. Sorry, I skipped that. I forgot about that a little bit. So you can see now that these illustrative pathways that have been in blue in the first matrix, they are now just sketched on a time as time series, and you can see that we've got like a new one sitting down here based on SSP1. And for you, I think it's important to sort of understand what has to go into these scenarios to make it happen. You know, basically, very quickly, for the SSP pathway to meet the 1.5 degree target, coal without CCS has to be phased out in 2050. And another thing that is extremely important is that that's basically the prerequisite for these pathways to work, is that there has to be a really growing, increasing share of CO2 sequestration, so carbon dioxide removal of one way or another. So these 1.5 degree pathways, they do not assume any geoengineering method, but they do build on a lot of BECCS. So the bioenergy carbon capture storage thing, and this is taken just out of Yuri's paper, and it's very busy, but there's just two key figures that are important, basically, that these numbers are positive quite extensively. That's percent change of afforestation and reforestation in 2050 and 2100. So there's a lot of afforestation and reforestation going on in these scenarios, which is obviously a very strong assumption. And the other one is that the change in cropland is supposed to go down. So due to efficiency in agriculture, we need less space for agriculture that may be filled with afforestation to draw out the CO2 from the atmosphere. So you can see that there's really strong reductions in how the cropland in 2100 will look like compared to today. And that's obviously, that's something to think about. You know, it's not necessarily completely unrealistic, but it's a very strong assumption. And I think I deleted it first because it was, I thought, even more confusing. But the right dashed line here basically shows the amount of cropland currently in Australia. So basically, in some of the scenarios, to meet 1.9 watts per square meter, whole Australia has to be removed, you know, to meet the afforestation, reforestation areas to get the carbon out of the atmosphere. Not Australia, but the cropland. You understand what I'm saying, I hope. So, not, you know. All right. So let's get to the final bit of our presentation. I've already alluded to the fact that we have now we are lucky to have extensions for the SSPs as well, and there's a very good reason for that. And I already talked a little bit about sea level rise. So I've done an analysis later last year where I looked more closely into the sea level rise part of things based on the SSP scenarios. And you can see that the 2100 response for GMT, global mean temperature on the left, and sea level rise, even in very strong mitigation cases, is very different. So we have a stabilization almost or not almost, we have a stabilization with regards to GMT, with regards to temperature, but you can hopefully see that even in the lowest cases for sea level rise, we still have an increase. So the sea level is not in equilibrium whatsoever. So we have to look further into the future to get an understanding what will happen post 2100. And that's why, one of the main reasons why we've thought about, Marta has been thinking about extensions very deeply in the last couple of weeks. And now it's Zeb's turn again to walk you through that. And then I think you have enough to think about.
Yeah, so this is the last little section, and then we'll move into questions. I'm sure there'll be a few. I've got a few. So basically, in the up to 2100, the IAMs quantify the scenarios, and they give you a huge amount of information about GDP, population, regional splits, all these sort of separations in how things divide and how the world looks. And then at 2100, they stop modelling for a whole bunch of reasons, which can be talked about another time. But at that point, we don't have a model to tell us, how should these emissions evolve consistently over time. So what we do is we say, well, we need extensions to look at how the climate might respond in the long term, but we're not integrated assessment modelers. So we make some really simple assumptions to allow us to develop scenarios which extend to 2300 without putting a whole bunch of assumptions in there related to a field we're not experts in. And you'll see how simple these assumptions are in the next few slides. And you'll see the importance of having extensions out to 2300 by the end of this talk as well, I hope. So the first one is fossil CO2. We do something quite simple here. We basically take our 2100 emissions. If they're positive, we bring them to 0 in 2250. If they're negative, we keep them at their same level until 2140, and then we bring them to 0 by 2190. All right, not much modelling in there, nothing too clever, easy to explain, and really useful for looking at how the climate might respond in such idealised situations. We've moved on to land use, and again, here it's even simpler. Everything goes to 0 in 2150. The idea being that we want to avoid eternal deforestation or assuming that our forests will take CO2 up out of the atmosphere for the rest of time. And so we need to have some kind of semi-sensible assumption. And you can see the dash lines, the RCPs were in some sense slightly more complicated in their extensions, and we've moved back towards simpler assumptions in this set of scenarios. For non-CO2 emissions, the assumptions are pretty simple again. We have, if you're looking at fossil emissions, they come to 0 in 2250, regardless of the scenario. And if you're looking at land use, the emissions are constant for the rest of time. And this is because they're related to agriculture and food production, and we don't have any sort of information about population or GDP, etc. So we just make this very simple assumption so that we can have a look at what the scenarios may look like. And so now we get to the interesting bit. And what we've done here is taken our very simple climate emulator, which we maintain here at Melbourne, MAGIC, and we've looked at the global mean temperature response and the sea level rise response for these scenarios and their extensions out to 2300. And for global mean temperature, we see that in basically all the scenarios, global mean temperature stabilizes. There's clearly a very big difference in the global mean temperature anomaly they stabilize at, and that has all sorts of policy implications. You can see down here that really the only scenarios which are even close to Paris are these three, so RCP 2.6, SSP 1 2.6, SSP 1 1.9, and really the only one which is actually Paris compliant is SSP 1.9. I want to draw your attention to this scenario in here, which is the overshoot scenario. And in particular, the fact that despite the fact that it hits well above the Paris climate agreements in 2050, by 2150, it's back down at a similar level to the SSP 2.6 scenario. And so we see that at least in the global mean temperature response, there's not this path dependence or hysteresis. If we look at sea level rise, the story is really quite different. And this is one of the most important things about these extensions, is we get a chance to look at the difference in key climate variables and the difference in their response to the different pathways. And so we have a similar story in terms of the spread of scenarios. But here you can see the overshoot scenario. And here you can see SSP 2.6. And that's, Alex, correct me if I'm wrong, near enough half a metre of sea level rise difference. And that's related to the way that sea level rise responds very, very differently to radiative forcing and energy imbalances compared to global mean temperature. And in particular, the fact that in the overshoot, the ocean has absorbed a much, much more heat, and so will continue to expand throughout 2300. The other important point to note is that none of these are sea level rise stabilization scenarios. So despite the fact that global mean temperature stabilizes, even in the best case, we're still rising slightly for the next 200 years or so. So that probably covers the extensions, the simple assumptions we've made, and gives you a first glimpse of how these might look. It's really important to note that there are huge teams all around the world building much, much more comprehensive climate models than we run that will give far more regional information about precipitation, rainfall changes, all sorts of climate variables we don't model. And we really look forward to seeing those results as part of the AR6 development process. And that's probably a good point to end on, that this is in some sense the most exciting part of the framework, is that it provides a way to combine all of that climate research that's been done with the RCPs with all of this socioeconomic research which has been done with these SSP narratives, and then provide a huge amount of information with which to look at the assumptions and the development of the 21st century. So with that, Alex and I thank you all for coming, and I think we'll move on to questions. All right, do you want to jump up and we can tag team this with the twins? Alrighty. Nita, do you want to fire away? We'll hold for the microphone, and for the people on Zoom, if you could say your name and your affiliation, that would be great.
Thanks, Seb. Thanks, Alex. Anita from the Climate College. That was really useful. Can you flick back, Zeb, to the SSP matrix, please? Yep. So I wonder if you can just, either of you, talk through a little bit. So obviously some of these compatibilities are, well, some are incompatible. So you can't have a sustainability scenario with really high radiative forcing. Similarly, you can't have some of the, like the fossil fuel development or the regional rivalry with really low radiative forcing. So the blue ones are the ones that are selected going forward. So I guess my question is a little bit more about how you see over the SRES, RCPs and now SSPs, the evolution of the use of these scenarios to the climate community, whether they make whether they're more or less useful to different types of analyses, given these different types of approaches to developing them.
Maybe I can start, and then you fill me in if there's more. I think traditionally there's been this, not the divide, but you had the social, sort of the social community that would look more into the narrative side of things and how that would impact emissions, for example, and you had the climate community that was really interested to finding out differences in the climate response for maybe even closer, very close pathways for different reasons, because the pathways look different, for example. And I think it's fair to say that this matrix now provides hopefully all of the stakeholders that are interested in looking at these pathways, providing them with what they need to pursue what they want to analyze. So if you want to, we have briefly talked about the overshoot scenario with this similar radiative forcing level in 2100, for example. I think that makes a key point. So we have two pathways that meet the same radiative forcing level in 2100, and this gives, for example, the climate community a lot of things to analyze and to run and to think about, because of the implications of just the different shape of the pathway. However, the whole narrative development side of things has also been improved, and I think it's now much more comprehensive to tackle different issues. I don't know. At the moment, there's still improvement, because I think none of the scenarios includes geoengineering, for example. So that's something that people just still, they're not really prepared to touch yet. But that's probably something, or maybe something, that will come in the next step at some stage, where you just have like some sort of geoengineering pathway. But this has been, I think for many reasons that go beyond sort of the capability of a scientist, like just a climate modeler, they have been left out.
Yeah, thanks, Alex. I think the only other probably important point here is exactly as Anita was saying, that there are certain scenarios you can't get certain forcing targets with. These white cells in the overview paper, this O'Neill paper, they make the point that what they're basically hoping is if you want to look at, for example, a SSP3 world with a 4.5 watt per meter squared radiative forcing target, whilst you don't have that scenario exactly, you can use some climate information from, say, this one and the old RCP 4.5. And that's the desire, and why there was quite a lot of focus on making sure that we had similar forcing targets, even though the pathway might be different, and there's questions about how much that matters or doesn't. So we have some information, but not perfect information.
Anita, do you want to add on the geoengineering in the scenarios? This is another information. There's GeoMap, which is another intercomparison exercise, and they add on different storylines for geoengineering. This is technically the scenario map, so it wasn't part of the mandate. I can inject one other little anecdote before we come to the next question, and to the online viewers also the option to ask questions. But who knows why RCP 2.6 or the 2.6 level sometimes appears in the literature as RCP 3PD? You're quiet. I need to know. So just as a little anecdote, this scenario has been like any, or this level has been decided in a 2007 meeting in Noordwijkerhout in the Netherlands. And probably on this jacket or others, there's still a bit of blood left because we had quite extensive discussions. There were two options, 2.9 and 2.6. And so for those of the more veterans in the community, I was kind of the spokesperson for the 2.6 group, and it wasn't pretty. But what we came out of that meeting in Noordwijkerhout in 2007 was because the scenarios were not really formalized and had to go through yet another approval process in higher governments, etc. So we left with a notation of 3PD. And 3PD stands for 3 watt per square meter, and then peak and decline, which 2.6 is more the level that you reach by 2100. So I left Noordwijkerhout meeting with the immense gratitude of having secured these two letters, PD, peak and decline, because the 2.9 would not have been a decline, and by that we managed that one. This one, by the way, is in the original O'Neill paper. The matrix stopped here. There was no 1.9 scenario. There was no 1.5 degree scenario. So this was another meeting in Luxembourg where Yuri and myself were the spokespeople, still left, probably blood left on the other side of the jacket. And so in order to be consistent with the Paris Agreement, we argued quite strongly that that matrix has to be extended, and it's very nice to see it now extended. Anyway, this is just an anecdote.
Thanks for the anecdote, Malte. Alexi Trundle, also from the Climate College. And I have a focus more in adaptation, which is where I sort of wanted to throw this question. So if it's a little bit beyond the brief of the talk, I'm sure Malte might want to chip in again. But I mean, I think one of the interesting things for me is that when doing adaptation work, a lot of those sort of exactly what that matrix is showing was previously done through a series of very coarse assumptions, sort of saying, right, so you're a coal port and you want to use a lower emission scenario. Well, you're probably not going to exist under that scenario. So you have to plan for something more realistic, for example, as a sort of a real world application that was done on that front. So I was wondering if either of you, or perhaps Malte in the wider discussions and negotiations, have seen any changes in the way that adaptation tools and sort of methods are developing that are trying to take into account this new approach, the more integrated assessment model.
I think that's beyond both of our remits. I don't know much about coal ports and adaptation, unfortunately. Do you want to say anything about the blood and where it came from? That's a decline. Malta's dealing with online supporters. So I'm sorry, I'll take that one on note and try and get back to you probably.
Yeah, it would be really interesting to dig a little bit more deeper into that. I know that there has been a paper that solely focuses on the narratives. So there may be much more information hidden in this one paper by O'Neill in 2017 that I will give to you, where they really expand on what will happen under each and every narrative. So it's just a whole paper just sort of going into the details, what the assumptions are like. I can imagine that there's some, in particular because we have this adaptation mitigation matrix and that we've showed, not matrix, but that graph where you can see where each and every SSP is sitting with regards to the challenges. I think there will be at least some information, maybe not on a local level, but you know, what tools they use to assess adaptation needs, or you know, the implications for that community too. So I'll get back to you on that.
We have an online question. Robert, if you can hear us, do you want to speak now?
Yes, I do. Yes, I can hear you. Yeah.
Can you speak a bit louder? We can hear you faintly.
Sorry, I must be my computer.
That's better.
Properly. Can you read my question out?
Yes, the floor is yours.
Oh, okay. It's a beautifully complex subject, but how do I explain it to someone who's uninitiated in the whole deal? How do I explain it to politicians who don't want to hear the story?
That's a very good and important.
Can you hear me?
Yes, I've heard your question loud and clearly, and it's a really, really important one. I think it's key, and obviously in this talk we tried to provide you with details. So it's been really packed, and there's been a lot of numbers and acronyms and assumptions, but it's probably key to break it down and more move towards sort of the last slide that we've shown, where the whole scenario history is sort of a little bit explained, as in that there's been two communities working relentlessly on improving the scenario side of things, and that we've now come up with a framework that can pretty much, can't cover everything, but it can cover a lot more than previously. And we have the chance to address the climate targets that are part of the climate negotiations. And we can also, based hopefully on the whole climate modeling exercise that will be happening until 2021 or so in the next coming years, we'll be able to address regional questions. And these regional questions are then, I think, they may be trigger points for local politicians or something, hopefully. I hope. Helps, yeah.
Thank you.
Hey, Alex Norton from the Climate Energy College. I just wonder a little bit about the lack of feedbacks in these integrated assessment models, whether you could just say something about that. Because obviously the feedbacks can be really important, whether they're in the human part of the system or the natural part of the system. Are there any groups around that you know of that are doing sort of modeling that include these feedbacks, or are they kind of done on a case-by-case basis, like we know of this feedback, so let's look at it?
This is beyond my expertise as far as I'm aware. There's not, but I mean, it's clear, right? There's big questions around, could you sustain this sort of GDP level we saw in SP5 with 8 degrees of global warming? And so there's clearly questions around that, but this sort of research is definitely beyond what Alex and I do. But I think it's a clear example of questions to be asked. One of the nice things about the framework is that you can say, okay, well, let's take this SSP5 world and apply a forcing target or an overshoot. And then you start to get, in some sense, you can look at worlds where the climate is actually potentially more realistic and more compatible. And that's one of the really nice things about the framework, is they actually include, here's the storyline, but let's look at different climates within that storyline. And so you can ask those sort of questions, not directly, but in some sense indirectly.
Thanks.
Maybe Malte, you can also provide some information on this, because this is potentially like the expansion of scenarios in the future. Potentially this is something where another step of improvement can be made in the next generation, even if we think about that perhaps that you have that cycle included in the IAMs. You know, you have MAGIC currently provides the climate output for this kind of effort, but it doesn't cycle back into that whole optimization process. So maybe that could be one thing that could be improved in the future.
No, it does. So all the IAM models, the 5 image, for example, and IAM, etc., they include a simple representation of the climate in their model, which mostly is MAGIC again. We provide them with a module and they include it. And so there are some feedback loops. I know for some in the agricultural areas, like is it viable to do agriculture, maize production or so here and there are some, and also there's a huge, but more like you say, it's a more separate, disjunct research group on the socioeconomic impacts that are resulting from 4 degrees of warming, etc. And so, for example, Anders Levermann at our partner institute there at Potsdam, he has a whole separate research group just looking at supply chains and how do the supply chains alter in high warming scenarios. Katja Frieder, who also was here from Potsdam a couple of times, they have also some work looking at different sectors and how they are impacted on the climate. So that's the ECMIP project, the cross-sectoral intercomparison project for different sectors. And so more and more of the integrated assessment models like image, like message, etc., they include sporadically more and more of those feedbacks. So it's not a yes or no answer, it's an evolving issue to include more of those.
Graham?
Hi, Graham Palmer from the college. You want me to go back to the matrix again? Yeah, thanks. One of the really difficult things is differentiating between what are baseline and what are mitigation scenarios. And there's been a lot of discussion around 8.5 and what it really means. And that's based on a return to coal, which my understanding is that went back to the 70s when there was an assumption of coal to liquids. But looking now, even with or without climate mitigation, coal to liquids doesn't look all that likely. And because the coal resource base is just so huge, in theory, we can get these very high RCPs. Have you got any comments about that? How do you differentiate between baseline and mitigation and these scenarios?
Yeah, maybe I can. It's actually a very interesting point, and it's also good that we may have the chance to clarify a couple of things with regards to that. So the baselines, the process that has been used to develop those SSPs was to go from GDP assumptions, population assumptions, these kind of things, then combine that with the narrative, the logic behind how the 21st century evolves, and then you basically directly go into the baseline. So you arrive with that, or you arrive at the baseline, wherever it gets you. It may get you to around 8.5, but also much lower than that, you know. I think, do you know by heart what the radiative forcing was for 3.4? Yeah. Other way? Right, yeah. That white cell is the baseline. Yeah. So you don't necessarily always end up, the baseline scenario doesn't mean that you end up with a worst case scenario that is as high as 8.5 watts per square meter or something. And also what is important to note is actually the return to coal is not assumed by SSP5, but by SSP3, because there's, I think, again, I guess it's a financial issue that, you know, coal is the only viable, affordable energy source, and you can also, you could see in all these time series that SSP3 doesn't end up as high with regards to the radiative forcing, you know, the baseline scenario at least, as SSP5. So SSP5 has like all the fossil fuels possible, basically drawing like all the reserves and then some plus renewables, and just to meet that incredibly high energy demand. So yeah, so you start the baseline for each and every SSP starts at different levels, and then you go down with these SPAs, these shared policy assumptions, and chuck in like levels where you like improve the policy internationally, where you go, you know, collaboration is it's a global effort, you know, it's strong, and then I think there's 3 or 4 assumptions on how these SPAs are implemented, and then get you down towards this one, you know, where you can then go, all right, with the SPA level 1, we get to, you know, we get basically to 6.0 watts per square meter in 2100. And then if we go even stronger, we may reach 3.4 watts per square meter. So I agree, it's really complicated because it adds another dimension sort of to this whole discussion. But hopefully it's a bit clearer now.
Yeah, sorry about that. Thanks very much for the presentation. As a newcomer to this, I've found it interesting, but I certainly agree with that question you had before about how you make it simpler for the average punter and also possibly for politicians, because it's very complex, and I certainly appreciate your efforts to try and explain it to someone like myself. There was one thing I was thinking about was all of your modelling, you've looked mainly forward, but how do you ensure that the models themselves are actually got any validity? Is it possible to go backwards and see how those models would be applied for historical data, as opposed to just trying to go forward? And particularly there was a slide right towards the end where there's lots of things happening from one point to another point, and then before and after there was sort of almost like just straight lines. And everything seemed to coalesce.
Yeah. So I just wanted to quickly get your name and affiliation, Mike.
Yeah, Mike.
Do you have affiliation? Was it
just retired?
Yeah, beauty. Thank you for coming down. It's really awesome to have people from outside the academic sphere here. So I think you asked a really good question about validation. I think for the climate models, it's something which is done really heavily is a comparison with observations, especially over the 20th century, especially the late 20th century, where observations are much better as satellite observations come in. For the IMs, I'm not sure. And this is a question I've actually no idea about, whether they simulate, you know, the observed emissions of the 20th century at all. They may do. I've never seen that sort of analysis, but I haven't looked either. I think your question about what happens beyond 2100 is really good, and that's the whole point of the extensions, is that we don't have models to create these kind of, you know, wiggles which you see with all the various interacting bits. We just have to say, well, we don't have the models. Can we make some assumptions which are easy to explain and give us at least some climate output to look at? And that's why you see, you know, in particular for CO2 land use, things are wiggling around and they all just go boom, 2150, they're all 0. And that's part of the difficulty of, you know, making different communities work together. The fact that the climate community wants output out to 2300, but the IMs don't model that far out. So what do you do as a kind of hybrid approach in the middle? And I think, you know, that's a really tricky part of the whole process. And I think you raise a really good point.
Yeah, maybe just again to your initial comment about the complexity and how hard it is to basically communicate that whole thing. Maybe one could say, you know, that you sketch different by sketching different societies for the 21st century. You try to investigate what has to be done for each and every society to get to a certain climate target in 2100. You know, if you want to meet Paris, what has to be done in these different societies? Is it even possible? As you can see, for SSP3, it's not possible. You know, if we run down that track, we won't get there anyway. There's no chance we will meet Paris. So I think maybe that's an easier thing if we think about the societies first. You know, all the different things that go into how a society works, where we get our energy from, you know, how we consume, these kind of things, and what these societies then have to do to get to a certain warming level in the end, you know, because this is in the policy space usually what people use to quantify climate change.
Yeah, I wonder if I can just jump in to underline what Alex says. So in a previous life, my job was working for the Federal Parliament, advising members and senators on climate and energy. And so when the RCPs came out, part of my job was trying to explain this to politicians. And one of the things that the RCPs and now the SSPs gives us that we didn't have previously is that previously we had very sort of determined scenarios where we could use them and put them into models and study the risks and try to understand them better. What we have now is not just scenarios where we can do that, and we do. There are different representative pathways that we can use to understand those risks and refine the science. But we also have a normative aspect, a political aspect, where we can look backwards and say, okay, so if we accept these risks that we're now trying to understand, what's the type of world we want to get there? What trajectory do we want? Do we want the regional rivalry? Do we want inequality? Do we want sustainable development? And we can make the decisions. We can reverse engineer these pathways to understand what decisions politically we need to make to reach them. So that's how I explain it to the politicians.
That's a great. Thank you, Anita. That's very helpful, I think. Yeah, thanks for that.
Please join me in thanking the speakers and Anita and others again, and our online people. Thank you so much for a fascinating seminar. There is lots of stuff to be figured out, broken down, put into simple language. Think not only about the politicians, but also about the people on the big boards of corporations who have not even heard about what is radiative forcing, or probably they just have heard about temperature and warming in 2 degrees. Anyway, that is a rich treasure of work that you presented, and thank you so much. Thank you.